All right, so welcome to part 2 of the titration videos. So these are 4 repeat titrations. I still use 10 milliliters of the calcium and magnesium water sample. I'm still using EDTA to titrate into them for my burette. The difference now is instead of using the ammonia to buffer the solution to pH of about 10, I added 30 drops of sodium hydroxide according to the procedure in Harris, which means our pH of this solution is about 12-ish to 13, somewhere in that range, right? So it's a couple of pH units higher than the previous titration, which means I can't use Ariachrome black tea as an indicator anymore. There are questions in your report about this as to why. Keep in mind we're now at a pH of like 12. That should indicate to you why Ariachrome black tea doesn't work anymore. So look into the sort of chemistry of Ariachrome black tea, figure out why it doesn't work at a pH of around 12, but it would work at a pH of around 10 to bind to the metal ions and give you this color change, right? So the color change here is still the same as in the previous set of titrations. It's just hydroxynethyl blue works at higher pH values than Ariachrome black tea. So I started with my sort of pinkish red this time rather than the wine red. And I'm starting to get purple color here. My endpoint that I'm still going for is still blue, but it's more, it's a different color blue this time around. It's more of a grayish blue rather than that sort of dark, vibrant blue in the previous set of titrations. So this is really close. I think I'm almost there. I'm going to add maybe another drop. This color change is just way, way harder to see than the first set of titrations, right? But the sort of goal in this titration is I'm driving the pH up to a higher value, so around 12-ish, 12 to 13. And in doing so, it allows for me to isolate and analyze for just one of our metal ions in solution. Right, calcium hydroxide and magnesium hydroxide have different KSPs. So, and by different I mean like orders of like 10 to the 6th or so different in magnitude, right? So what we're doing is we're basically masking one with sodium hydroxide and allowing us to analyze for the other, right? So the previous set of titrations allowed us to figure out the total concentration of calcium and magnesium in solution, and in this titration we're just analyzing for one of the two, right? And then since you know the total, and if you find out one of the two, well, the difference would be the other one, right? So you'll have to look up the KSPs of calcium hydroxide and magnesium hydroxide as part of your report, figure out which one I'm actually analyzing for here, right? And then as your report, you'll know the concentration total and find the independent concentrations of the calcium and the magnesium that are in solution. So this is my first titration, right? It's very distinctly blue, but it's not as pronounced of a blue as it was in the previous set. The indicator just is a different shade of blue, or right. So I'm doing the same technique as before. I recorded my endpoint volume. I'm adding a drop to see if there's a significant color change. And if there's not, I'll use the previous one. I think there was a bit of a one in this one, so I'm going to kind of keep going. Right. I'm going to record again, like read the burette, record the volume, do another drop, read the burette, write it down. And so I'm sort of here just like adding volumes as I go until I think I get to the final endpoint of blue, right? So yeah, this titration, it's still the same color change. It's just harder. Like the colors aren't as pronounced. It's just not as easy of an endpoint to see. So these ones take me a little bit longer. I'm being very methodical in add a drop, record the volume. I think I'm at the endpoint. Record the volume, add a drop. Maybe not. Add a drop, record the volume. Keep doing that until I'm satisfied that I'm adding a drop to this thing and I'm not seeing any color change, right? And it's not picking up in this video how subtle the color changes are. Like, to me in lab right now, this thing still looks purple. In the camera here, it looks bluish right? And you'd think we're done, but when I'm adding these drops, I'm still seeing color change happen where they land, right? Um, so this sort of technique of record the volume, add a drop to the still solution, does the drop, where the drop lands, do you see significant color change? If yes, I'm not at the endpoint yet, right? So I don't know if you can see on my sheet here to the right or to your left, but I've written down, I think, 5 volumes as I think I'm super close to the endpoint here, but I'm not quite getting it. So I'm like writing a volume, recording it, right? So this time I added a drop. I didn't see a color change where the drop landed, so I'm done, right? And so I now have 1 titration, and now I know this volume, so I know about how long these next titrations are going to take me. And I think of memory serve, these take like 10 milliliters, whereas the first set of titrations took like 20. So I don't need to refill my burette as I go between here. So I'm now staring up because I know how long my titration is going to take. So I'm just going until I'm about at that endpoint. Right? And you can see where the stream is landing. You're starting to see blue form. Give it a swirl. Now we're back to red. Right? But the chemistry is the same here. It's still EDTA reacting with free metal ions in solution. Once it runs out of those free metal ions, it will start displacing indicator, which is why we start seeing a color change to this sort of purpley and then eventually to blue as the EDTA is sort of yoinking a magnesium or calcium, but whatever metal ion from the indicator. And so we have free indicator in solution, which looks sort of grayish blue in color. Right? But yeah, because we are at a higher pH range, we can't use Ariachrome black tea, so we're using this hydroxynethyl blue. Sort of just the pH range dictates which indicator I get to use. Right? But yeah. So the rest of the video was just me continuing to do the next couple sets of titrations. So I'm struggling really hard to see the color change here, right? Like in this video, that kind of doesn't look like blue. That just kind of looks like gray. So I don't think I have enough indicator for my eyes to perceive what color this is. So I just add a smidge more. I think Harris says to add about 0.1 grams to each flask. I think I realistically added about 0.2 to 0.3-ish to each flask. Just the color change is super subtle in this titration compared to the first one, right? So I just brought that over. You can see that was more distinctly blue compared to this, which is kind of a grayish purple. And I'm looking at this thing at different angles to try. Right? You just saw me squat down to look through it the long ways. The reason I'm doing that is an application of Beer's law, right? Longer the path length, the more light absorbed, the darker or more vibrant the color will appear to me. So I'm trying to do this to just get an idea of what color this thing is, because for a while this just looked gray to me. But I'm going to keep doing the titration. I'm going to add a little bit at a time. I'm going to compare to my first trial. I'm currently staring at my volumes, seeing, hey, where I'm at on my burette, does it make sense? Right? Employing the same sort of tactics you guys do when doing titrations. So I'm letting this surface just sit still, adding a drop, watching if it changes color where it lands. So I'm adding 2 or 3 drops here because I am seeing color change. Right, that's starting to finally look more blue. Right, tap off my drop, rinse my sides down. Right, comparing my 2. You can see this is just harder to do than the first set of titrations. So recording my volume, I think I'm done here with this one. But the remainder of the video is me doing 2 more trials. Oh, I wasn't quite done. But the remainder of me is me doing a couple of more trials. I think I screw up the 3rd one badly. I get really close to the endpoint, and then my hand just twitches, and I open the stopcock the whole way up and just let a stream of water in when I'm right at the endpoint, and scrap that trial and go do the 4th. Right, but I think I'm finally here recording my volume. But yeah, so I'll just for the rest of this video, spend time talking about the report instead of talking about the titrations. You guys know titration technique by now. Partial drops, swirling, rinsing everything down into the flask once you think you're close to the endpoint. But yeah, so our goal in the first set of titrations, to reiterate, is again to find the total concentration of metal ions in solution, both the calcium and the magnesium, right? Both of them are readily soluble at a pH of around 10, so my EDTA is reacting with both of them, right? Chemically, what's going on here is in the burette, I have protonated EDTA, right? It's disodium EDTA, like dihydrate. So really the EDTA is partially protonated, right? 2 of the sodiums are in place of some of the hydrogens in the structure, but as it hits our titration solution in the Erlenmeyer flask, right, that's buffered to a pH of 10, or in this case a pH of around 12. So those hydrogens that are still, those acidic hydrogens that are still attached to the EDTA, some of them deprotonate and get the EDTA in a form that it can actually bind to these metal ions. It forms a complex with said metal ion, and the last of the acidic hydrogen sort of pops off and is freely floating in solution. Of course, that immediately gets picked up by, the hydroxides that are in solution, since we're buffered at a pH of like 10, right? But all of those all the chemistry that I just talked about happens in an extremely short time frame, so there aren't issues with like kinetics going on, delaying my color changes and whatnot, right? Yeah, this is, again, I'm super struggling to see the color change, so I'm adding a little bit more indicator just to sort of see, and it's like purpley gray, so I'm adding a little bit more. I'm just trying to add enough indicator so that the solutions don't look gray to me, but they look like a colored gray. So I have something to actually work with. But so yeah, these second titrations, I'm still using EDTA. It still deprotonates as it falls into solution. The difference here is I'm only analyzing for one of our 2 metal ions. One of them is significantly more soluble at a pH of 12. The other is significantly less soluble at said pH. So this allows us to sort of mask one of the 2 ions and analyze for the other. Right. There are some questions in the report about the colors of the Ariochrome black tea indicator and why we can't use it at this now pH-ish of 12 plus, 12 to 13-ish solutions. So what I encourage you to do is go look at the chemical of Ariochrome black tea. Go look at the structure. So there's my hand slip, and I've gone way past my endpoint. And I'm actually not quite sure because I'm still struggling to see color in this one, so I kind of struggle with it for a bit. I add some more drops and whatnot, but I eventually just scrap it. I overshot the endpoint, I think, by a whole milliliter or so. But anyway, go look up the structure of our Ariochrome black tea. It has some acidic hydrogens. Go look at what their Kas are. Figure out, convince yourself why you wouldn't see a significant color change at a pH value of around like 12 as in the second titration. Like, why do we need to actually use hydroxynaphthyl blue instead of Ariochrome black tea for the second set of titrations? In addition, in one of the report questions, it asks, like, hey, why do we have to even buffer the solution to pH of 10, right? These metal ions solubility changes with pH, but also does Ariochrome black tea work in certain pH ranges? Which pH ranges does it work in, and why? So convince yourself of that sort of information. Why do we have to buffer these solutions? All right. So my third titration was bad. I threw it out. and I do one more here that ends up being pretty good. In the data set, if you look at my relative standard deviations for the first set of trials, so the ones where I used ammonia buffer and I used Radichrome black tea, my relative standard deviation for those trials is significantly lower than these trials. And that's probably mostly due to my struggle to figure out color in these second trials. The color changes are just not as distinct. They're not as obvious. I still got relatively good standard deviation, all things considered, but it's definitely, I'm definitely more confident in the first data set where I was using a Radichrome black tea indicator. And a lot of that is just familiarity. In general chemistry, every year we do an analysis of like calcium water using Radichrome black tea, EDTA, ammonia buffer, the same exact titration. So I'm more familiar with that color change. I only do this quant one, once a year. I do the Radichrome black tea one 2 to 3 times a year. So familiarity is definitely an advantage if you're trying to drive down standard deviation of your trials. Right? But yeah, sort of as this closes out, again, comparing to my other ones, still has a little bit to go, but as you guys are working through the report, as you have questions, shoot me emails. I'll be, keeping an eye on my email over the next couple of weeks. If you have questions about any of this stuff, feel free to reach out. I'm happy to help. But yeah, I've sort of cut out quite a bit of the report from what we normally do. Since you guys didn't actually collect the data, normally I have the Thursday and Tuesday sections compile their data, and then we do t-tests to compare, hey, did the Tuesday and Thursday data, are they statistically the same or not? This year, I'm not having you guys do that since you didn't actually collect the data. We'll just use my data. You'll calculate what concentrations I have of metal ions total, of calcium, and of just magnesium. And then I am having you do one t-test, but that is comparing it to the masked out calcium and magnesium concentrations that I had to make the solutions, right? So assuming, I think there's a question that says, assuming that those masked calcium and magnesium concentrations are infinitely accurate, do a t-test from the titration data to compare to those, right? But yeah, I'm sorry you guys didn't get to actually do this titration in person. I hoped you've enjoyed my excellent titration skills. But yeah, it's been a great semester working with you guys. Email me again with the questions that you guys have. So thanks for watching.